Okay, so for my final project, I decided to remake one of the models from our previous labs and then compare it to real life. So I ended up remaking the bullet impact lab um, by recreating my own bullet in SolidWorks and then importing this into Abacus. So this bullet here is a 5.56 millimeter M193 bullet, which will actually be shot in real life. So I then ended up creating a plate that would actually be shot within Abacus. And this is another plate that's going to be shot in real life. And this is a 20 millimeter thick plate that is made out of aluminum 6061. So one major issue I ran into right off the bat was that meshing the bullet created an error when trying to run the program due to the fact that some of the elements near the tip of the bullet near this reference point here would get so deformed. And then the program would not run due to the fact that they were so deformed and Abacus would just crash. So to counter this, I ended up treating the bullet as a rigid body. So essentially meaning the deformation of bullet can be neglected due to the fact that I honestly don't care about the deformation of the bullet. I only want to compare the deformation of plate to real life. So moving on to the property section of the model here, I made the plate out of aluminum 6061, and this is shown right here. So as you can see, the general density for aluminum, the modulus of 68 GPa, Poisson's ratio, all that. But one weird type of plastic deformation, if you remember from the lab, was called the Johnson-Cook dynamic failure model. So initially, I didn't really understand what this was. So there's always like D1, D2, D all the way through D5. And these are actually 5 damage parameters that need to be accounted for in the plastic deformation of the plate for aluminum. So this can actually be found just in a research paper. So as you can see here, D1 is the initial failure strain, D2 is the exponential factor, D3 is the triaxiality factor, D4 is a strain rate factor, and D5 is the temperature factor. And these are all tabulated very well in many research papers for aluminum by itself, which was pretty easy to find and very nice to have. So once all the properties were inputted, I put the bullet and plate into an assembly, just shown here. So pretty simple with the assembly. I first use a rotation mate to rotate the bullet to the correct orientation to hit the plate perpendicularly, which is along the z-axis, as you see here. Then next I use a translation mate to move the tip of the bullet into the middle of the plate and the middle of this circle. And this circle is very important for the meshing portion of this model, which I'll explain in a little bit. So after this, I created a new step that is called a dynamic explicit step, shown right here. So there are numerous reasons I chose a dynamic explicit step over a dynamic implicit step. So first and foremost, the explicit step requires much less computational time and power due to the fact that there are many less equations that need to be solved during the analysis. And with these large models of upwards of 10,000 and 12,000 elements, as you'll see, the time and amount of equations for each element begins to matter more and more. So one other thing that's necessary to know about an explicit dynamic step is that the time increment can't be too large because otherwise the solution becomes unstable and the error increases exponentially, leading to an unrealistic model. So there's something called the largest time increment that is calculated by Abacus and is referred to as a stable time increment that Abacus holds in here. So once this dynamic step was created, we move on to the interaction portion. So I began by adding the interaction constraints between the bullet and the plate. And here I essentially just created a friction coefficient between the two parts. And this coefficient of friction was determined by finding a coefficient of kinetic friction mu sub k in the copper plating of the bullet, shown on this plate here, and the aluminum plate that it is shot through. So there are many different results for this friction coefficient when I looked it up, and it ranged from about 0.1 to 0.6, depending on some outer factors such as if the material is wet or dry and so on. So I ended up choosing a friction coefficient of 0.5 since the materials were dry and they're actually shot in real life. So that is shown right here. Next, moving on to the boundary conditions in the load section. So there are only 2 boundary conditions I actually needed for this model. Starting off with the encastre boundary condition, this essentially fixed the plate in place by allowing no translations and no rotations to occur. This is essentially just because in real life, the plate will be mounted and will not experience much deformation outside of the bullet hitting it. Next, I also created a boundary condition shown here, which makes it so the bullet can only travel in the U3 direction or the Z direction as shown here. So the bullet can't rotate or travel in the X or Y direction whatsoever, and just hit the plate perpendicularly like it will in real life. So lastly, in the load section, I created an initial velocity for the bullet, just specifying initial velocity for this reference point here, and that's in the predefined field manager. So as you can see here, I made an initial velocity of 970 meters per second in the V3 direction, which is the Z direction, and that's the initial velocity that the bullet will have once it hits this plate. So moving on to the meshing portion of this project, I wanted to create a much finer mesh within the center of the plate where the bullet will travel through. And this is because there won't be much stress and deformation in the outer areas of this plate where the mesh is much more coarse. So there's no reason to have a fine mesh out there. It just increases computational power and time. So that is the reason for the circle in the middle of the plate that I showed you earlier, just so I could seed that circle and make a much finer mesh within the center. So one problem I ran into here is the type of element I was using throughout the mesh. So I began by using hex-dominated elements. So this worked okay, but I understood that there's a symmetrical bullet going through a plate at a perpendicular angle. So therefore, the deformation that when the bullet leaves the plate must be nearly symmetrical, a little mushroom cloud all around where the bullet left. Using hex-dominated elements, I found that the deformation was way off in terms of being symmetrical. So I then changed the type of element to a wedge element, and that is shown right here. As you can see, it's much more symmetrical, although it did add a bunch more elements generated on the plate. So this change helped a lot, as the deformation looks a lot more on what I expect compared to the hex-dominated elements. So another issue I had when meshing the part was the amount of elements within the thickness of the plate within this 20 millimeters here. So at first I only had one row of elements. As you can see, there's 5 currently, but at first I only had one row of elements. So that's the entire thickness of the plate. This made it so the deformation was essentially non-existent, and there was no mushrooming when the bullet left the plate. So I understood that this was not very realistic. So instead I began to add more seeds to the edge of the plate to give more elements throughout the thickness of the plate. So as you can see here, there are 5 elements which made for a much more realistic deformation of the mushroom near the hole. So I ended up having to use a lab computer to actually do this, because as you can see, there's about 13,000 elements here. And on the student edition, I can't run this. So I have some videos that are shown here. So here is the model as predicted by Abacus. So just as a reminder, I treated the bullet as a rigid body because I was more interested in the deformation of the plate. So as you can see, the bullet actually takes some of the plate with it as it leaves the opposite end of the plate, which is very interesting because I kind of thought about this in essentially real life terms. And it did make sense to me because there will be some shrapnel that begins to fly as the bullet exits the plate, just like in real life, as you probably haven't experienced, but as you've probably heard of in movies or just in general. So that is very interesting there. Next, I want to compare it to the actual deformation that we shot in real life. So as you can see, we shot one at 25 yards, one at 50 yards. So there's about an 8 millimeter mushroom all around the bullet. This is from the exit of the bullet, and it's about, like 8 millimeters tall to from the back of the plate to the top of this mushroom. And that'll be explained later in the mesh convergence. So as mentioned, I want to do a little mesh convergence study to see how many elements would be able to accurately predict the deformation. So as you can see, I have numerous videos of different amounts of elements in the plate. So first is about 1,700 elements, and as you can see, there is not much deformation whatsoever. It's a pretty terrible model and not very realistic. But once you get up to 2,600 elements, it gets a little better. Still not great, but you can start to see the mushrooming around the bullet as it leaves, but still not too realistic. Once we get up to about 4,300 elements, though, you can kind of see an actual mushroom all around as the bullet leaves. And this is starting to get pretty realistic, starting to drag some pieces of the aluminum plate with the bullet, and that is from the friction coefficient there. And as we keep going up, all of it looks pretty similar to the 4,300 elements that you just saw. So in an actual mesh convergence study, here's the amount of elements versus deformation predicted by Abacus. And this is against the actual deformation as seen by the plate, the 8 millimeters. So as you can see in this mesh convergence study, anywhere above about 4,300, 4,500 elements will nearly mimic the actual deformation found in real life. So there's not much use in going above about 4,500 elements because that'll just add computational power and time. So one odd thing that I did notice in real life was that, as you can see here, 25 yards, the bullet is actually not in this copper plating, but at 50 yards, the bullet is in this is still in the plate here. So I tried to model this in Abacus with a slower velocity just for fun to see if the computational model in Abacus would kind of simulate the bullet getting stuck. And it actually worked, which is really cool. So as you can see here, I shot the bullet at about 200 meters per second initial velocity. And yeah, here you can just see it actually getting stuck and just staying within the plate, which I thought was really interesting. And I kind of want to look into it more, but I just don't have time right now. So I couldn't quite accurately model the bullet getting stuck at the lower velocity that would occur at 50 yards as compared to 25 yards. And I believe this is because I modeled the bullet as a rigid body that wouldn't deform. But in real life, the bullet will deform after hitting the plate since there's a lot of energy lost and therefore wasn't able to make it through the 20 millimeter thick aluminum plate at 50 yards. So overall, I feel like I learned a bunch about how dynamic models work in Abacus since we didn't really work with that too much this semester. And it was really interesting to kind of dive in and see more realistic models and how dynamic models work in computer software and how they're able to simulate actual events. So throughout the summer, I think I'm actually going to try to continue to model this and try not to model the bullet as a rigid body, but instead model it as a deformable solid, because I feel like there's a lot of energy lost as the bullet deforms, and therefore the bullet would not be able to go through the plate at certain velocities as it does now. So thank you for listening and hope you enjoyed.